I now want to remind us of a few things about angular momentum. So this is, I think, stuff we talked about towards the end of 117. I know that was a while ago, so let's just recap the highlights. So for a point particle, right, we talked about you can define the angular momentum of a particle, L. It's a vector, and it's a cross product, R cross P. Let me say a few things about this. So let's imagine we have a particle here, and the particle has some momentum that looks something like this. So the particle could be moving in any arbitrary way. Doesn't have to be going sort of moving in a plane or moving in a circle, but what we do need to have is an origin. So if I have some origin here, all right, the r vector point goes from my origin to my particle. You can see from this picture that the value of L is going to depend on your choice of origin. But if you have an origin specified, so in this instance, right, R cross P points out of the page. So because, right, when we're mostly going to restrict ourselves to thinking about motion in a plane, right, we can get away, as we do in a lot of rotational dynamic stuff, with thinking basically about just like the in plane or the out of the in or out of the page component of L. So we often get away with just thinking about one component. With or rather, it's sort of magnitude. So well, it's not well. We might have to worry about signs. We're not going to for the time being, but we can often get away with ignoring the vector nature of L. Now, a few other things, right? This may not be the most common way you think of L. We often think about L for like rotating objects, and so I think you can sort of see how this comes in. If you had your particle here, let's say it was moving in a circle, we can think about L for a rigid body. Right, and so the simplest kind of rigid body might be something like masses, sort of like a dumbbell, where let's say you had masses connected by a lightweight shaft to an axle. So something like this. Right. Where if this thing is rotating, sort of, it's typical to pick, it'd be to pick the axle or the axis of rotation as my origin. So let's imagine this was rotating with some angular velocity. So for a rigid body, right, you know that we might have talked about L equals I omega, where I is the moment of inertia or the rotational inertia of my rigid body, which accounts for how mass is distributed in my rigid object. Now, where this comes from, we probably didn't do this derivation in detail, but it's not so hard to do. Basically, you apply R cross P to each of the masses in your object, and then you pop out that L goes like I omega. So why angular momentum matters is the angular momentum principle, right? And we probably did talk about this briefly. So just like there's a momentum principle that relates changes in in momentum to an impulse, there similarly, right, it turns out that changes in the angular momentum of a system have to do with a net torque acting over a time interval. So I think Bohr called this an angular impulse, or in differential form, right, dl dt equals net torque. So that was a quick refresher on angular momentum. Let's see now what angular momentum looks like for the electron orbiting in a hydrogen atom, and what predictions the Bohr model makes about the electron's angular momentum. So if I have my hydrogen atom with my proton at the center and my orbiting electron, we can ask what is the electron's angular momentum if we choose the origin to be at the proton. What is L of electron? Okay. We're assuming a circular orbit here, right? So the radius of the orbit stays constant, right? So we have just r sub n, right? The momentum, so that's just going to be the magnitude of the momentum of my electron, which is going to depend on which orbit it's in. So formally, right, you know that a cross product goes like, magnitude of A times magnitude of B times the sine of the angle between them. But notice that for circular motion, right, the electron's momentum is always tangential, right, and it's going to be perpendicular to the radius vector from the origin. So the angular momentum is going to be just the magnitude of the r vector, which is r sub n, times magnitude of my momentum times sine of 90, which is 1, or just r sub n times p. Now, it turns out the quickest way to see where this comes from is to use de Broglie. So de Broglie tells us, right, he tells us that the wavelength, right, is going to be equal to h over the momentum, or magnitude of momentum. However, we also have, right, that quantization condition we invoked in deriving the radii. And that quantization condition, right, remember, was that you have to fit an integer number of wavelengths around a given radius. So you have, right, we had the n times lambda, right, where lambdas are electron de Broglie wavelength, equals 2 pi times the nth orbit radius. Well, put these two things together, right? If I put those together, I can find p in terms of r sub n. So if I solve this for lambda and plug that in here, right? So lambda, I get 2 pi r sub n divided by n equals, from up here, h over p. So that now lets me solve for p in terms of r sub n. So if I just multiply p over and shove all of this stuff on the left over to the right, so that gives me p equals h times n over 2 pi r sub n. But you know that h over 2 pi is h bar. So this turns into h bar n over r sub n. So now if we take this result for the momentum and plug that in here, right, we get the following. We get the electron has an angular momentum of magnitude r sub n times h bar n over r sub n. Look, the r sub n's cancel, and we get that the angular momentum is equal to n h bar, right? This is an important result, right? It says that the electron's angular momentum can't take on any value. It can only take on discrete values. So h bar, 2h bar, 3h bar, etc. In other words, the electron's angular momentum is quantized. I might need to get a new marker in a sec. So even though there's much about the Bohr atom that is not sort of physically correct, electrons don't live in fixed orbits, this result that L is quantized turns out to be one that still carries over in the quantum mechanical treatment of hydrogen.